Thanks so much for the kind introduction, and thanks a lot to the organizers of QHack for inviting me. I have not yet had the chance to speak at this great event, but I love the enthusiasm that it builds. I love hearing people that look forward to this event every year, so great job, and I hope I can contribute a little bit to the content of this wonderful event. And so today I'm happy to tell you about some of our recent work in the sort of attaining quantum advantages in learning from experiments, and the notes I have on how this relates to concepts of dequantization. But really I want to kind of say that, it's exciting for me to present this work because it represents a really nice buildup for me of conceptual advances that I had personally, not just in kind of the details of the technical work, but also it kind of changed my philosophy on science a little bit and the way that I view quantum computing. And I hope to be able to share even a little bit of that enthusiasm with you today. And so I'm going to start off by kind of framing the type of problem that I want to talk about today and putting it in the context of quantum machine learning and I think what I would call sort of a data advantage as opposed to a computational advantage. And so often when we talk about quantum computing, we think about problems that are computationally limited. And by that, I mean, it takes some simple input and there is at least a known, if very expensive, computational procedure that goes from that input to some output. So you can think about like keys to factor or some Hamiltonian to simulate, where at least in principle, some procedure exists that you could do it on, say, exponential time on a classical computer, but we would prefer it if a quantum computer could do this in some very low polynomial time, even preferably linear. And so we often think about these as the quintessential advantages for a quantum device. And kind of the trouble with this, of course, if you're trying to demonstrate a quantum device's advantage, is that you're always competing against advances in classical algorithms and larger supercomputers. And today I'm actually going to focus on a slightly different type of problem, which you can phrase in many ways, but for the purposes of machine learning, I'm going to call data-limited problems. So these are problems that are limited by the availability of data, where no computation is possible to overcome the lack of data that you have. And so in this situation, and I'm going to detail this a little bit more, we imagine ourselves in a quantum scenario where you're going to get limited copies of some quantum state you're interested in, possibly transducted from a quantum sensor, possibly just coming out of another part of your quantum computer. And in this situation, what we'd like to see is that even a minimal amount of quantum processing can reduce the number of copies of this data from like an exponential amount to a more reasonable polynomial amount. And part of this motivation comes from our recent work looking into data-assisted problems. And so this is a class I only kind of became aware of recently through our explorations. And it's basically similar to the first class, which is data-assisted, which is computationally limited problems. We have some known computational procedure, but if I give you a little bit of data, I can actually make that problem easy and remove the need for a quantum computer for certain problems. And so just to kind of motivate that a little bit, to give you a little bit of framing, and I think this is an important point, especially for a quantum machine learning crowd, let's imagine that we have some circuit that we're going to have, and I promise this is one of the more technical, although basic slides in the talk, saying that basically I have some, quantum neural network and some input that I'm going to assign into the amplitude of some quantum state. So even if you don't know the details of this, you can just think this is P numbers I'm plugging into my quantum computer. And my task is going to be to compute some output defined by this very long quantum circuit. And this is just, of course, some Hermitian observable and some, I'm going to say, arbitrary length quantum circuit. So this function should be at least as hard as BQP and as hard as very, very long quantum circuit. So basically, this is saying I have an encoding of this data in some sense, or rather an encoding of the observable that's at least as hard as direct simulation of the hardest quantum thing I can think of. For example, this could be, if P was 1, I could just make this an instance of the factoring problem, and this would be incredibly hard. But now I'm going to say, okay, well, I'm going to give myself some data. So some examples from this problem. And once I have that little bit of data, what can I say? And if I relook at the definition of this problem, and if I rewrite this just a little bit, I find out that in fact that function can be re-expressed in this form, where all of that complexity of the horrible quantum circuit that I wrote down is lumped into these BKLs, and it's just this kind of simple form. And so when I think about this for a second, so again, even if this was one by one, I could have put Shor's factoring algorithm in here and it would have been hard to evaluate. But once I gave myself a little bit of data, say as a treat, I learned that this is at most a quadratic function of x with p² coefficients. And so really the bottom line of this is that for this kind of very toy problem where I've made it simple with no data, this is a hard quantum circuit that I think is incredibly hard to evaluate, even for a classical supercomputer. And with a little bit of data, a polynomial amount of data in my input dimension, this is an almost trivial learning task. And so this is meant to kind of caricature a bit the situation, which is if you restrict the domain of your problem a little bit, very hard quantum circuits can become very easy things to learn. And it's not sufficient for an encoding to be difficult for the problem to be difficult to learn. And so this was kind of a starting point for us to kind of launch off and try to understand more generally how data changes the complexity of problems, especially in quantum machine learning. And in this paper that I'm kind of only mentioning as a setup, we kind of quantify this difference in complexity class where being endowed with some amount of data raises your ability to do this kind of computation and really opens up new problems. And kind of following on this, one of the lead authors on this work went on to write a different paper. You might ask, what kinds of problems are learnable from data? And in fact, many problems that we identify as important problems in quantum computing might fall within this class. For example, they showed that there are certain classes of ground state problems that if you were just provided a little bit of data about the ground states within each phase, that these things become efficiently learnable. And for the purposes of this talk, then you might ask, is the fate of quantum computers just to provide training data for classical models, which based on that last slide, we now think of as more powerful than kind of classical algorithms that are not endowed by data? And you're like, okay, well, that makes them incredibly practical and useful, but that's kind of depressing for one of the world's most advanced technologies that we've worked on to date. Shouldn't there be something a little bit more amazing that we can do with this rather than just provide training data? And true to form, some of the same authors went on to write other papers showing that, in fact, there were models where if you were able to keep around a little bit of quantum data at the same time, you could start to learn things that are essentially unlearnable in this single copy sense, and you can't really get them without a quantum computer. And what I want to do today is kind of build on that work with some of these collaborators and boil it down to what is the bare essential of seeing this kind of advantage and of using a quantum computer to learn about my physical world or collect data and build models that are simply not possible without quantum computers. And so I'm going to talk about two different settings today. One I'm going to call the quantum enhanced setting, and one the conventional setting. So the conventional setting, we imagine there's some experiment where either I have, molecules or planets or black holes or maybe something like this interacting with a sensor of some kind. This could be a basic, photodetector or something like that. Could be a quantum sensor of many spins that retains this information. And I'm going to get some information from that sensor. And in the conventional scenario, I'm going to imagine that I get one measurement from that sensor at a time. So basically the sensor comes in, I do any quantum circuit I want to it, but only on a single copy, and do any measurement I want to those qubits. And in contrast, the quantum enhanced scenario, I'm going to allow myself to keep around one extra copy of this quantum sensor state. So basically the state's going to come in, I get to shelve at least one copy of this in my memory, I get to collect another one, and then do joint measurements between the two. And this will be the essential difference between this quantum enhanced scenario and this conventional scenario where I collect classical information. So this is just to kind of caricature this classical memory state. I'm getting one at a time, destructively measuring and storing this information. And this is akin to kind of what you would do in a laboratory today if you were just, say, doing a spectroscopy or laser experiment, things like that. And in the quantum case, I'm going to allow myself to keep one of those copies around before I end up processing. And similarly, I can do this not just to individual quantum states, but I can instead prepare a sensor, expose it to some quantum process or other process, bring it back to myself, and then collect the state of that probe that I sent out to look at the process. And in the quantum enhanced scenario, I'll allow myself again to store a copy of that probe that I sent in, where now this physical process is denoted E. And in this work, what we did was spend a lot of time boiling down to the most basic version of this advantage that we could find, so we could sort of understand its essence and really get it on a device and understand, well, at scale with realistic noise that happens to real quantum states, is this still a feasible advantage that we see? And basically, we're going to show that there's an exponential advantage with exactly 2 copies on 2 different tasks experimentally, and it retains efficient classical compute. So we don't acquire some strange overhead that we have to overcome either. And so with that, let's get to what is the simplest task we can have an advantage on. Perhaps there's an even simpler one, but this is about as simple as I can imagine. So our setup is that you're going to have n copies of this mixed state, which is the identity matrix, so like the totally mixed state, plus some contribution of a non-local poly operator, where P is some non-local poly. It could be like ZXZ or something like this, YXY. And every participant in this process, so the classical learner and the quantum learner, the form of the state is known, but this alpha factor and the exact poly that you are going to have in this state is unknown. And so something to notice about this state, maybe you've worked more with pure states than you have with mixed states, is that basically this state is unentangled, but is not factorizable. So in this sense, it is a state with essentially only classical correlations, but it has strong non-local classical correlations, and it's expressed in at least 2 incompatible bases, so the Z and the X basis. And this can be realized in a depth 1 Clifford circuit plus some classical randomness. So this is a super simple state to set up, and it's a super simple state to work with. And we're going to compare this setting of conventional experiments with quantum enhanced experiments. So again, this is, I'm allowed to look at 1 copy at once, or I'm allowed to get a copy of rho, so a realization of I plus P with some classical randomness, and then another realization of it where I keep 1 in memory and I then collect another before taking measurements. And my task is going to be something like, take any measurement you want on the n copy budget that I give you. So I'm going to limit the number of copies you're allowed to have. I'm going to collect some classical data signature of that state. And then given some new poly operator, I'll predict its expectation value for you. So once I've collected all the data collection is over, you hand me a completely new poly operator, or one that might correspond to P or not, and tell me what is the norm of its expected value. Alternatively, I might give you a problem where I promise you that one of them is the candidate poly operator, and you try to tell me which one of them has bigger expectation value, which should correspond uniquely to the one that is P. So just to kind of frame some things that are coming up, the quantum experiments, or at least the setup of them, some of their execution will be difficult, but their setup will be fairly basic measurements. So you might say, well, where did most of the work in this paper come from? And it came from showing that, in fact, once we've made this problem simpler and simpler, you need some technique for showing that the separation to the best possible classical algorithm is growing exponentially, including adaptive updates to that algorithm. Just kind of give you a quick glance at what is done here. It's basically the result summary is the best possible conventional scenario for that task I set up, scales exponentially in the number of qubits that define my state. And roughly what happens is you reduce it to a type of fancy discrimination task where you have some null hypothesis that the state is totally random, and the alternate one that it's this state that you're interested in. And basically, because of the simple form of the state, you can bound the optimal discriminating POVM, including its adaptivity, and any measurement you do gives exponentially vanishing returns. So kind of moving then to the simplest quantum enhanced experiment. So I haven't told you the details of the optimal classical strategy, but you can sort of bound the best it could possibly do. So the simplest quantum enhanced experiment is I'm now going to have these scenarios where I'm going to prepare these copies of my state rho, and on the first n qubits, I'm going to have 1 rho, and on the second n qubits, I have another rho of this mixed state. And remember, this is just depth 1 Clifford states plus randomness, basically, to prepare these. And the game that we're going to have to play throughout these experiments is we're emulating the process of quantum data collection because we don't have these sensors out in the wild. And so basically our setup is that we prepare these using known gate sequences, but then we blind ourselves and say, well, I don't know what state was actually prepared. And this allows us to kind of attain this advantage in an experimental setting before we have this kind of advanced sensor. And then after this, I'm just going to do a sequence of these bell measurements. So I'm going to do, say, like C-naughts and Hadamard, and collect these 2N bit strings. And these are going to create 2N classical bits that sort of are a sketch of this state row. And the kind of punchline of this is if you use this setup, there is an efficient scheme that is independent, more or less, in the number of qubits for the samples you require, and only has a roughly linear computation time in the number of qubits. And there is a way to compute these exactly by hand, but actually I'm going to focus not on that, but on the learning aspect of it. So to summarize the scales of separation between these two approaches for this one particular task, recall that my task is take any measurement you want on the N copies. And so that's confined to the conventional and quantum enhanced scenarios respectively, and then collect classical signatures of the state. So now I'm left with only classical information. All of the quantum is shut down. And now give me a new Pauli operator O to predict the state to a new error. And in the classical scenario, you need to achieve some fixed accuracy. You need an exponential number of these copies and measurements and bits. So therefore, to even touch any one of those, you're going to be spending an exponential amount of compute. And in the quantum enhanced 2-copy scenario, you're only going to need this sort of constant number of copies, depending on, of course, the precision as well. And so what I'm going to propose, though, is that bell measurements are not just something you could do by hand, but could be used as a feature in learning. So far too often in quantum computing algorithms, you see something like Shor's factoring algorithm or quantum phase estimation, and you're left with the impression that the phases need to be so exactly right, the algorithm needs to be so exactly perfect, that to actually learn something naturally feels almost impossible. It looks like you need serendipity to align in the phase coherences to show you the way. And so we wanted to show here is that these bell measurements actually carry enough information that I don't need to know the right answer, that I can in fact learn it very easily from this kind of informational sketch of my states. And so we asked, can we use such a sketch of these like bell measurements as a feature of a quantum state to learn this task? And this is important as well, because if we compete against classical algorithms, they could learn some noise or boost an adversary against us. And in fact, we want to do it both in a supervised setting on smaller sizes where we don't even have to have learned, where we have to know maybe labels of small things, but then see if it generalizes to large systems. And even in an unsupervised setting, so that's not data from this experiment, but I'm going to show you some unsupervised data later, where I don't even need to know the labels, but my data will show me that there is something worth discovering. And that will be a fun thing to see in a bit. And of course, I think we need to imagine this in a larger quantum data pipeline. So this means that if you step back and think, where am I getting this data from? I showed you a slice where we're going to be emulating it. So it could come from another quantum computation I don't know the details of. It could come from an analog quantum simulator where I have a method of transducing that data into my quantum device. Perhaps it comes from a natural quantum system where I have that kind of coupling, or some advanced quantum sensor of many qubits that collects light from the stars, and I can manage to use that in a coherent and interesting way. But inevitably, I'm going to need to transduce it. And so when I say transduce, I just mean move from one quantum medium to another. So say ions into superconducting qubits. And this is going to go into some kind of quantum buffer. And as far as we know, for more advanced processing routines, we're going to need to put it in something that's long-lived. So a quantum memory, and I don't mean QRAM here, I mean more like injected into the surface code. But this stage is essentially always going to be unprotected, at least as far as we can tell. You've built a sensor to the best of your advantage. Nature might not provide you with the copies that you want of a state to try to boost that up. Or you don't know any symmetries by which to measure and correct the state. So you're kind of left with that fidelity, whereas this side can become protected. And once it's in the quantum memory, you can kind of do whatever you want to it as long as you've gotten that code distance high enough before doing your data processing. But basically, because this is always protected, this is kind of relevant to the situation where you're going to have a heavy amount of noise coming in on this state, and you're always going to have some limited fidelity. And you want to know, do these things work in this scenario? So proofs have some experimental flexibility, but not unlimited. And for us, that means this is a great opportunity for a noisy quantum device to provide us some information on what can be done here and what the limitations of these techniques are. And so that's what we kind of want to do here. First, in the simpler experiment, before I jump into the more interesting one, is that I'm going to imagine the state preparation and the noise that's involved in there is this sort of transduction step, and the flaws in my processing are this finite transduction fidelity. And states are going to come in, and I'm going to measure, and I'm going to get 2 in bits out that tell me something about my state. And I'm going to lay it out on this Google Sycamore chip, where I'm going to separate system A and system B into red and blue and do this kind of checkerboard pattern. And you might squint at this and say, well, this is just kind of these kind of unentangled 2-qubit pairs across my system. And you'd be right, but interestingly enough, as long as you blind your state in this case, that's enough for a classical learner to still not be able to overcome this gap, so long as they don't know the exact preparation details of rho. They're allowed to know the general form and everything else, and that's not enough. So let's now go to the task and see how well it does. So again, I'm going to get n copies of this state rho, and I'm going to be given 2 candidate Pauli operators, and I want to determine which one is larger. And I'm going to train this on a gated recurrent neural network because I want to see, if I only see small instances of this and I don't know the right And what we basically do is train this on noiseless data, less than 8 qubits. And whenever I say qubits here, that's per subsystem. So that's a 16-qubit experiment. We train this recurrent neural network, and the result is quite striking. So let me walk you through what's happening over here. We have the ability to bound the best possible classical answer through these techniques, and that's this dashed line. And what I'm showing here is the number of samples required in a learning algorithm to achieve an accuracy on this problem of is A or B bigger of greater than 70%. And this classical lower bound, you can see, just goes straight up exponentially. And then these quantum enhanced 2-copy experiments, even with a noisy device, comes down here and learns this task extremely, extremely well. And so you have a multi-order magnitude difference at this 20 qubit size. So that's 20 qubits on 2 subsystems, or 40 physical qubits. And again, this is a data advantage. So if we're in this scenario where you don't know the state and the copies are limited, there's no amount of classical supercompute time that can come and overwhelm you. And you might ask, well, how do the real classical samples perform? So it costs exponential, of course, to process them because there's that much data. So you can only do it for a few points. But this is kind of the separation between practical performance, the best possible classical algorithm, and what the quantum one does on very, very simple measurements. And so you say, okay, well, that was interesting, but the experiments were a little bit simple. What else can you do that would really convince us it works on noisy data, and you could kind of learn something about the system you didn't know beforehand? So now we're going to take the process scenario. So instead of taking this quantum state from the outside and looking at it, I'm going to prepare a quantum sensor state, expose it to some process, take it back, and then sort of do measurements on it. And the task that I'm going to be interested in is, given access to a process E n times, determine if it's a random times reversal symmetric evolution, so kind of a random evolution, but with all real entries, no imaginary terms, or a random unitary, allowing the terms to be both real and complex. And the setup's going to look incredibly familiar. I'm going to, again, do one of the simplest possible things I can do, which is to create this sort of Bell prep. So I'm going to create Bell states, expose them to copies of these processes, and then collect my Bell sketch of this prepared probe state at the end. And this one's a little bit harder to set up because basically we have this pair structure here, but a totally randomizing subsystem structure here. So you can imagine this involves a lot of detailed work on layout, scrambling, and then kind of relaying out these pairs and doing the measurements. And unlike the previous case where we could do things in nearly constant depth for the state prep, including all of the different components, this is something that goes up to 40 physical qubits, 20 for each subcopy, and sort of 1,300 gates with a gate depth of 54. So this kind of pushes the limits of what we can really get signal from today, but helps you to show that even as you lose this signal, this quantum ability to learn things about your environment will persist. And so how do we How do we do that? So this is part of the part that I'm most excited about, which is, what if we don't know that, there's two underlying tasks, basically? If we were collecting this data from the universe and I put in almost no label information and I know almost nothing, could this actually enable discovery? And basically, we're going to sit here, and our setup is going to be, I'm going to collect these Bell sketches, so expose my sensor to the environment, take it back, take 2 in bits for each one. I'm going to repeat this 500 times each for the quantum enhanced case, 1,000 times each for the traditional case, so that the number of received copies are equal. I'm using 2 at once at top and 1 at a time at the bottom. And then I'm going to do something simple. For each one of those where I told you it was exposed to this process in particular, I'll take the expected value and the variance, and I'll have that describe that collection of data. And then I'm going to say that's a feature vector for each process, basically. And now I'm going to take this feature and do something many people in machine learning are familiar with. I'm going to jam it into a pretty standard machine learning kernel. I'm not going to put in any information about which process was which. I'm going to put it into this squared exponential kernel, and I'm going to do kernel PCA on it. So very few adjustable parameters here, very little information put in by the experimental team. And what's going to happen is that on the conventional side, you're going to look at both the dynamics done where there's 1D scrambling and 2D scrambling, and you're going to look at the first 2 principal components and look at this and say, well, the general one, so one with real and complex, is these blue diamonds, the red is the circles, and you look at this and you say, well, I don't think I can see any difference between the two. Maybe nothing's going on here. And then the striking thing is you put in the quantum enhanced data. Again, this is exactly the same setup between the two, only taking out these 2 in Bell state bit strings. And you can see that it more or less perfectly separates the two. And I was super excited by this because of this phenomenon I mentioned before, where everything seems to need to be so perfect in quantum computing. All of the phases need to line up, et cetera, et cetera. And then this is a setting where you can basically see that had I not known there were 2 distinct processes, I could have imagined learning that and digging deeper just from this unsupervised data. And it was something that was totally invisible without my quantum computer. And so this makes me really excited about what we could learn about our universe. And this is sort of the kind of quantification. So that was a qualitative picture. If you actually use this kernel PCA as a classifier, you can see how much more accurate the quantum enhanced setting is. But in the interest of time, I'll move to one more item, which is there was one thing we had in the paper, which I think is important to the future of quantum data pipelines. It's a little bit beyond the reach of experiments today, but I think worth pointing out, especially in the setting of quantum linear algebra, PCA learning, and dequantization, which is, like I mentioned, there's going to be this step in the process. If we're thinking about learning on quantum data, where essentially corrupted quantum data is going to come in. And, that's not our fault. We can only build sensors so well. Space has background fluctuations, things like this. And in some cases, though, you can actually model this as there's some density matrix that I get where you have some component of uncorrupted data. So say you did a really good job and your transduction fidelity is 90%. And then there's some component kind of orthogonal errors to this. And there's been a number of techniques. I'll just mention the one, say like virtual distillation, that gives you a way to sample from rho squared. So you can imagine that if you square this and the setup is correct and the fidelity is large, basically you enhance the uncorrupted component and you suppress the smaller components. And if you look at what technique does this, it's suggestive in the sense that it's exactly the destructive swap operation that I've been using this entire time. So somehow this kind of joint copy measurement is powerful in many settings. So this was used as an error mitigation technique, and it's kind of an interesting way to view different constructions. And if one swap gives you this virtual distillation that purifies the second order, you can kind of comb through the literature and recall that if you use swap as a generator, so this kind of infinitesimal generator, you actually get the quantum PCA algorithm. And so this work, we basically lean on these concepts and 2-copy to show that in a conventional scenario, an exponential number of copies are required to learn about this principal component versus only a constant number in the quantum enhanced setting. And so this means that this kind of quantum enhanced setting is one of the only possible ways we have to purify incoming data about our universe where the fidelity is limited by some natural construction. So this is once again sort of evidence that they can show us things that would be invisible without the quantum device. And so you might then say, well, now you're talking about quantum PCA. I've heard about this dequantization topic. What's the deal with that? Why can't you just dequantize everything you just did? And I won't get too much into this, but we sort of followed up with a work on dequantization to clarify this point that, you know, just to recall what it is. So imagine you have a quantum PCA or recommendation systems or some linear algebra problem, and you're allowed access to the data in some, you know, probabilistic form if you look at how it's laid out. And you can imagine different quantum access models where you say that, well, I'm going to take as quantum input because I need this thing to scale like log of the dimension, and encode this once again and say amplitudes, or use some implicit encoding, or that I got a data statement from rho. And we then say, well, if you're only getting this kind of QRAM model where I'm going to do a measurement and get out a result with some probability, then a more honest depiction of this is to say that I should be able to sample this oracle with some output probability, or I should be able to ask for the probability of some particular component, or know the norm of the state. And if under this model, which kind of more philosophically mimics a QRAM type model, I can achieve the scaling that I would like, say up to Pauli overhead of the quantum scaling, then I say that it's dequantized. But what you have to do here is be a little bit careful about the settings that you're applying it in. In particular, this second line, querying anything to arbitrary precision, is a bit of a dangerous one. And so in particular, we looked at this for a few different problems, in particular ones where this access model, basically if you hide something in this, just to kind of give you a very brief overview, if you hide something in the precision of the state, QRAM is actually weaker than the original classical oracle. And so this requires something like 2 to the n calls to prepare on the quantum side, or on the classical side requires only one of these accesses to query. So this is a case where by encoding into a quantum state and forcing yourself to use it, this SQ access, or the dequantized algorithm, was actually exponentially more powerful than quantum. But that wasn't because you couldn't do the classical algorithm on the quantum computer. It was because of the setup of the problem made this a little bit unnatural. So it's just a way of saying you have to pay a little bit of attention here. And the setting that we're actually in is closer to this implicit or data setting. And if you were allowed access to that very powerful query step, it can actually solve sharp P problems efficiently in one step. So that's not to say that dequantization isn't an important thing to think about, and there are setups where it does apply. But for this particular one, and in particular for this audience, when you're collecting quantum data, you have to be careful about that second assumption. Typically, allowing yourself arbitrary precision in a query is equivalent to needing an exponential number or more of copies of your state. And we clarify some of these arguments there. So kind of just the summary and outlook. I know I've gone a little bit over time, but I hope you'll forgive me. The punchline I wanted to hit is that if we could find, and that's a big if, you know, in bold here, a suitable quantum data source, our quantum cloud devices today allow us to learn things that would otherwise be invisible to us. And so, of course, recall that this computational versus data advantage, there's no amount of compute that I could go out and do and replace the ability to look at multiple copies, basically. And in this work, we had proofs of advantage in state learning, process learning, and quantum PCA with experimental demonstrations up to 40 qubits and 1,300 gates. And my hope is this work starts to inspire even more work on quantum data sources and sensors that are beyond quadratic. So if you're anything like me, I sort of had a bias that quantum sensing perhaps was a quadratic at most speed up. And for some tasks, that's true, but the speed ups appear to be more task specific than that. So if you get fancier and look at interesting learning problems, you can sometimes find these exponential separations like the ones here. And I wonder if we could find deeper connections between this and the experiments we already do in physics, like interferometry experiments that inherently come with 2 copies. I wonder if we can go beyond these Bell features and do something interesting on larger groups, and where these proof techniques can be applied otherwise. And with that, I'd like to thank everyone involved in the work, especially Robert Wong, who I think you've already heard from, who did all of the amazing work with the proofs and inspiring work previously, and Michael Broughton that helped to set up all the experiments, and Brooke that helped to calibrate everything. And of course, all of our co-authors who played a crucial role in shoring up the proofs, boosting the work, reading, and bringing this to the finish line. And with that, I'd like to thank all of you for listening, and I'm happy to take questions or move to the interview. Thank you.
Thank you, Jarrod. There was so much valuable information in 30 minutes. I may want to review it many times to make sure that I grasp everything. Thank you so much. Fantastic talk. I have one. I want to start off with a bit of a technical question. So, personally, I've been thinking a lot about this question of how do we best extract classical data from measurements made on quantum systems, right? And so there are techniques that have been explored, like classical shadows. One way that I would interpret some of what you have presented is that there's this idea of these Bell sketches, right? So maybe can you elaborate a bit more on why this was specifically kind of the technique that was suitable for this task? What makes it unique?
Yeah, absolutely. So it's a good question. This kind of what is the essential difference here between using and why did we choose these Bell sketches as opposed to other measurements that we could do?
Yep.
So it actually relates kind of to the specifics of the task we chose. So we kind of boiled things down a lot to these states that had this intrinsic Pauli structure to them. And actually, a series of proofs in Robert's other work had shown that, of course, if you have local observables that you need to learn, something like Pauli classical shadows is able to efficiently extract this data on single copies. And so then if you want to go towards observables that don't commute, as we do here, and you want ones that are non-local, so there are ways, you could be inspired, for example, by the early work of Scott Aronson, which said that quantum states are pack learnable. So there's some set of measurements that I could do, which scales only like low polynomial in the number of qubits, but maybe has hard computational procedures. But by restricting to Paulis, you can actually show that learning non-local Pauli operators can be computationally efficient, but requires this kind of scary majority vote scheme. But then you can kind of, when you restrict to just the magnitude, you sort of find that these two copy measurements, so the unique property of these Pauli states, and you can ask how well this generalizes as an obvious follow-up question, is that the Pauli group has a nice property that when you take two copies, every element now commutes. And so now when you want to measure all of them at once, what a Bell sketch gives you is in principle magnitude information on any Pauli operator, local or non-local, that you can have on your system, but it's missing sign information. And so this is what we leveraged in order to do this without needing things like majority vote, where we reduced everything to a magnitude problem. And the hard work to do was kind of show that was still hard, basically. Yeah.
I see. Thank you so much. I'm definitely intrigued to look into this a bit in more depth. Jarrod, you said that, or I guess you motivated kind of your excitement in this direction by saying that it makes you, again, excited on what this means in the ways that we can learn more about processes in the universe, right? So could you again maybe elaborate a bit on this? So what kind of processes do you have in mind, right? Of course, this particular case, I would argue, was kind of tailored specifically for proof techniques, etc., but then opens up this question of can we extend it elsewhere? So do you have specific things in mind?
Yeah, that's a great question, and it's one I've been thinking a lot about, but I don't know that I've reached super satisfactory answers yet. So in particular, I'm kind of hoping this work motivates the development of quantum sensors that are kind of naturally more multi-qubit. So what I mean by that is there's, of course, a lot of work on quantum sensors that use things like GHZ states, but they're effectively using many qubits as one to enhance sensitivity. And so I'm kind of curious about where there are setups in nature where you could have a many qubit quantum sensor that's really bringing in many pieces of information about your system. And so you could think about, say, NV centers in Diamond are often used as a sensor. And if you could distribute those throughout a system, then have a spatially resolved NV kind of sensor that you would use in magnetometry or something like that. So basically, something you could then place in a chemical system to learn about a process, or you could place in an interesting physical process. I think some of the most quantum states we have are, say, things coming out of particle colliders, things like that. Could you put a sensor next to it that could learn correlated information about the particles coming out that might, because of their origin, be naturally entangled or something like this? And of course, you can think very far into the sci-fi future, say put a Dyson sphere of qubits around a black hole and see what you construct out of that. But I don't know if that's super practical.
It's good to think big, that's for sure. All right.
I'd say along the more practical side would be, we have, say, these growing analog quantum simulators where we'd like to both remove errors from them and learn about the intricate physics happening. Yes. And that's probably a shorter path towards transferring that information into a digital computer. So, yeah.
Fascinating. Jarrod, actually, as part of our questionnaire, you mentioned, and I'm quoting you, that you were excited about the fact that some of your recent work has changed your philosophical outlook on the way we do science and advance, right? So you get me by mentioning some philosophy. Can you maybe, again, expand on this? What do you mean by changing your philosophical outlook, and why exactly is that the case?
Yeah, thanks for the question on this kind of speculative topic. So I actually, after doing, collaborating with Robert here on the original Power of Data paper, I really started to realize that I'd taken a very computational view on the universe and maybe computational is too broad of a word, but I started to think that, if we could sort of compute well enough, understand renormalization groups well enough, that we could really do these interesting computations that jump between length scales, say that jump between chemicals, proteins, DNA, cells, emergent life, things like that. And when I was looking at these results that really showed that being endowed with data, say if it comes from a more interesting computational source, really boosts you into a new complexity class. But then more generally, even if that data was produced by an efficient process, but one that kind of bifurcates so randomly, that really as scientists, we're benefiting from data in a way it's hard to call it computational in the sense of I would follow a rote experiment. I can actually follow the path the universe took, and that cuts down the number of things I need to look at dramatically every time I stand up and look at my physical universe. And so I really started to think that conceptually viewing science as closer to machine learning than rote computation was more appropriate. And so there were probably people out there that already had this advanced philosophy before me, but personally, I'd always thought that there was this road of using computation on, say, even quantum systems to get all the way to the emergence of life that made sense. And I started to say, well, I don't actually think that's the case. I think now that we learn from the choices the universe makes, and we can actually use that to boost our ability to do science and discovery in ways that isn't possible from closing your eyes and computing in a math cave, basically.
I mean, that's amazing, right? Because I could argue that the scientific method is about learning from experiment, but this is kind of taking a different twist by thinking also about the role that computation plays in it, right? I interpret it to be actually close in spirit to the idea of learning from experiment, right? It's just thinking more broadly and how we process that information. Right?
Absolutely. And I think part of the part that pushes it into philosophy, so, it's easy to get in trouble with computer scientists by talking about this, but part of the part that changed my, part of the part that gets interesting is that, formally there are these problems that are called undecidable. So we don't think any finite time algorithm can solve them. And advice. And so what we did was show is that data was a restricted form of advice. Advice can, in a toy sense, break this undecidability. And so if you take a few leaps and you say, well, I don't know anything about halting problems. There was a series of works by, maybe series is too strong a few works by a guy, Chris Moore, that gave sort of a physical definition of undecidability and mapped it to cellular automata. And basically what it is that a system with dynamics, where as you're marching forward in time, there's a sudden qualitative change that no finite time computation that you could have done would have told you that change never would have happened. And if you start internalizing this, you look around and you say you can be a bit flippant about it and say, is there any finite time computation I could have done on the dinosaurs to know that post-extinction, humans would have emerged? And you say that a reasonable person would say probably not. But, by looking at the data, we can say that humans are definitely here and work in that universe. It kind of solves an undecidable problem for us in some very hand-wavy approximate sense of what complex life emerges. So, yeah.
Wow, so from Dyson spheres on black holes to the extinction of the dinosaurs. I love it. Jarrod, maybe one last question from my side before jumping to questions from the audience. You mentioned again that you were once given the advice to not pursue a career in quantum computing, right? And I think that's a theme here at QHack, also learning about people. So can you tell us about that story and what made you disregard that advice?
Yeah, so to give a little bit of background story on this. So I was a graduate student not that long ago. And even back then, so I think the year was, just 2012 or something like this. Even then, the attitude was quite different about quantum computing in the US and maybe other places as well, which is that it was still a very speculative endeavor, and that honestly, even government funding agencies were a little bit afraid of it, in the sense that small efforts had been tried before, they had funded it and saw that it was difficult to build devices, difficult to make progress. And so they quickly retracted their funding. Lots of professors on tenure track didn't get tenure. And you kind of had these multiple waves. And so there were a few people still sticking with it. So in my graduate group at Harvard, we had some postdocs who had been in quantum computing for a while. And some of them would wander around kind of late at night saying, there are no jobs in quantum computing. Like, if you want to feed your family, do something else. Kind of things like this. And so it's very discouraging. And you look at the state of affairs, there were very few industry jobs at that point and very few academic jobs. And the ones they had were like soft money professorships and things like that. And so in truth, I spent one foot still in quantum chemistry, one foot in quantum computing for most of my grad career. And even as I was leaving graduate school, I was considering like data science fellowships and things like that. And it was kind of at the last minute that I got the Alvarez Fellowship offer, which said, you can have a little bit more time to do quantum computing. It looks like the tide is changing. And I don't think I'd really been aware of that at the time. And I was like, okay, well, I'd like to spend some more time on it. Even if this doesn't end up working out, I can kind of work on something else. It'll still be interesting. And somehow, very dramatically in that period of time, experimental advances, industry investments, and things kind of exploded overnight. And suddenly it went from a field with no jobs to a field with great opportunities all across the board, academia, industry, etc. And this just sort of happened by accident. I don't claim to have any foresight in this topic. I just was fortunate enough to work on something I like and then have the world agree that it was interesting in some way, which is, a nice situation to be in. And I guess sometimes in life, you can just follow the opportunities that present themselves and you get lucky.
Yeah, wisdom. There was this undecidable problem: is Jarrod going to go into quantum computing? And we just waited and got the answer, didn't we? Thanks.
Indeed.
Yeah, thanks, Jarrod. So a few questions from the from our audience. So Broken Atlas, you kind of expanded on it, but I think it's going to be good to maybe answer it directly. So the question is, what do you see on the horizon that excites you the most?
Yeah, what do I see on the horizon that excites me the most? I mean, in truth, more recently, this kind of ability to learn from experiments excites me the most, and kind of what we could conceive of as a quantum sensor, or even as a quantum state that I would want to provide to one of these processes. I mean, if I once again tempt the ire of computer scientists, there was this groundbreaking result in computer science recently. It's in the last year or two by Thomas Vidic and a number of other collaborators, where they showed this somewhat cryptically named result, MIP star equals RE. It takes a lot to break down the actual details of what this implies. But if you close your eyes and don't worry about, being attacked because you live in the woods like me, basically it meant that, if two things came down and they solved these unsolvable problems. So you can imagine the universe is trying to show you something that is utterly inconceivable, like these solutions to halting problems or proofs of them, basically. And you could entangle these sources of things that the universe wants to tell you and probe these entangled provers. They could convince you about something about the universe that is utterly invisible or mathematically impossible without it. And I take that as a very blown up theoretical version of kind of the stuff that I just talked about, which was a little bit more finite size and grounded. But there are aspects of this universe that are absolutely untouchable without quantum technology. And I hope even if we can't find more rote uses of, say, data processing of applications or ad click-throughs, that excites people enough to really want to keep going on this. So.
Wonderful. Jarrod, unfortunately, that's all the time we have for today. Thanks again for the fantastic talk. The talk. I really think the information density was so high. Thank you so much. It's a pleasure having you here. Yeah, and have a great day.
Great. Thanks a lot for the invite, and thanks to everyone for listening.